So today we begin with Chapter 5, C Functions. So we have already looked at a lot of programs as examples for different concepts that we have studied in previous chapters. But in the real world, programs are usually much larger than the ones that you've seen. Now, not every program, actually, most of those large programs are not written from scratch, from absolutely no building blocks. And uh, as a matter of fact, we use a divide and conquer approach to write programs. Many tasks have to be repeated, which means the code for them can be written once and can be packaged into into what we call a function, and we can then call that function repeatedly, again and again, wherever needed, and we only have to write that code once. And we've already been doing that for quite some time now. So, in this chapter, we basically look at some of the features of C language that make it easier to design, implement, operate, and even maintain large programs. And like I said, in C, the principal tool that we have for that are functions, the ability to uh, put pieces of code into functions. Usually, when you write a program, it's usually some combination of new code that you write, and the code that you write is divided up, organized into new functions that you will be writing. But alongside that, you will also be using pre-packaged functions that you get with the C standard library. So the C standard library is basically a collection of functions, and any place on any compiler that conforms to some standardized version of C, you will be able to find all of those functions in actually even in standardized in standardized libraries with the same name. And it doesn't matter if you're sitting on a Windows machine, or if you're sitting on a Linux machine, or even sitting on a Mac or any other platform. As an example, the kinds of functions that you can find in the C standard library can, for example, there are some mathematical libraries that allow you to do some math calculations. There are functions for string manipulations, character manipulations, input, output, and a lot of other useful stuff. In order to become a good programmer, you should always be aware of what's already available in the C standard library. And the point is that there's really no purpose or no benefit in reinventing the wheel. If something is already available in the C standard library, you should use that function, because that function has been used extensively, has been tested extensively, and is usually written by experts, and is therefore also much more efficient, or more efficient, or at least as efficient as what you can write. Out of all these three, I think the one that should be most important to you is that it is well tested. And if you use functions from the C standard library, that will make it easier for your program to compile on other platforms. And that's what we call portability. Now, I've been using the word function for quite some time now, and I've been referring to printf and scanf and even the power function as functions. That's because they are functions. Okay, and these are printf and scanf are part of the standard IO library. The power function, which we used very recently, is part of C's math library. And we'll look at a lot of other functions that we have in the math library. So you've already been using functions, but so far we have been using functions that are in C's standard library. We haven't written any function of our own. And that's what we'll do in this chapter. Writing your own functions. And to differentiate them from the functions that we have in the C standard library, we call these programmer defined functions. So the beauty of using functions is that you write them only once and you can use them again and again. Kind of like the printf and scanf function, right? Somebody wrote those for you, put them in the C standard library. Now you just include the library at the top using the #include preprocessor directive, and you use it again and again, multiple times in the same program. You do not have to rewrite that function. And it's the same way with any function that you develop for yourself. You write it once, you can call it again and again. And when you use it again and again, you do not have to worry about how the function works on the inside. It just does its job. You can think of that kind of like the way organizations work, the way management in an organization works. So let's say at the very top, we have a boss. And that boss has a job to perform, and he asks one of his workers, one of his employees, or maybe a number of employees, to do parts of that job. In this example, the workers are kind of like functions that the boss has called. And once each worker finishes his or her job, that worker will come back with the finished work, and that's basically the return value that you get from each function. And then the boss can use the work product from all of those workers to kind of perform the overall or finish the overall task. And those workers may in turn call other workers, put other people to work, right? It's not like it's only a simple hierarchy in offices. People have other people working for them, and those people may have other people working for them. So in this sense, you have workers working for other workers and so on. And the good thing that happens by that is basically you can hide the details of how functions do work, how work gets done. And there's a work for that. We call that hiding of implementation. Sure, there's also another word for it. Abstract. Sometimes it's also referred to as abstraction. So you can think of this scenario over here. You have a boss. He hands over some work to worker 1, some to worker 2, some to worker 3. And worker 1 in turn may divide up that work somehow and give some job to worker 4, some job to worker 5. Now, let me show you an example of a function from the math library that I just mentioned. There's this function sqrt that you see highlighted over here. SQRT is shorthand for square root. So when we execute this particular statement over here, this function will compute or return the square root of 900, which is 30, right? Which will be passed as an argument to the printf statement, which will print it out as a floating point number with 2 decimal places after the comma. In this case, 900 is the argument to the square root function. And like I said, for this particular example, the square root function will return the floating point value 30. More specifically, the square root function does not take a floating point, an argument of type floating point, but of type double. And the return type is also double, of course. However, whether the value is actually a floating point, the return value is actually a floating point number or a double, when we print it out using the printf statement, the conversion specification or the placeholder is still %f, as you know. Now this square root function is included in the math.h library of that is part of the standard C library. So let me show you a couple of other functions. So as argument to the square root function, you do not necessarily have to give a value. You can, of course, give an entire expression. So this one, for example, if C1, D, and F are all, in this case, floating point variables, let's say C1 has the value 13, D has the value 3, F has the value 4. You can put in an entire mathematical expression and pass that to the square root function. In this case, the value of C1 plus D times F would be 25, and square root would return the value 5.0. And here's a more extensive list of functions that are found in the math.h math library in C. So you've already seen the square root function, and what that is doing is basically computing this. Similar to the square root function, there's the cube root function. The cube root function computes the third root, of course. There's the exponential function, which computes e to the power x. There's the log function, which computes log to the natural log of x to the base e, or you can also write that as ln of x. You may have seen it like that. For log to the base 10, we have the log 10 function. To compute to get the absolute value of x if x is a floating point number, we have f absolute, floating point absolute, to compute so basically this thing, to get the ceiling, the next largest or the next largest integer value of x, the ceiling function. We have the ceil function over here, and over here in this last column you see a bunch of examples. So for example, if you pass 9.2 to the ceiling function, the return value will be 10. If you pass it minus 9.8, a negative number, the next largest integer will be minus 9. So take care of that. It's not minus 10, minus 9. Minus 10 is less than minus 9.8, right? Corresponding to that, we have the float function, which does the opposite, finds the next smallest integer closest to x. We have what we've already used, the power function, which computes x to the power y, and power function takes 2 arguments, of course. We have f mod, which is the floating point equivalent of the mod function that you've already, for which we have the operator, the percentage sign. So this computes gives you the remainder of x divided by y, where x and y are both floating point numbers. And then we have the sine, cosine, and tangent functions. So functions allow you to divide up your program into smaller parts, reusable parts. And inside of each function, it's kind of like a world on its own. You can create your own separate variables inside a function. Those variables are called local variables. And those variables are only accessible, visible, inside of that function, not from the outside. Functions, as you've already discovered, take inputs in the form of as parameters. And that is one of the means by which you can communicate with a function. This is how you can provide input to a function, data on which it can work, on which it can perform work. And these parameters that you provide create corresponding local variables inside each function. So there are several advantages to breaking up a program or functionalizing a program. First of all, you can divide up the job of building an application. So program development can be made more manageable. Once you have made a function, you may want to reuse it for a different project. So software reusability is another motivation for dividing code into functions instead of writing one large block, one main function that does everything. And this whole idea of reusability is actually one of the big motivating factors behind object-oriented programming languages like C++ or C# or Java. Each time you use the printf function or the scanf function or even the power function that you've just recently learned of, you are basically reusing somebody else's written function. This is an example of code reuse. Now, in this case, these functions happen to be part of the standard C library. But just like that, of course, there's always the standard C library, but just like that, you can write your own functions, which you or others may choose to reuse and save time on program development. And of course, there's the advantage that once you have written a piece of code that performs some useful function, a useful action, you don't have to rewrite it once you package it as a function. This is good advice. Each function should generally be limited to performing a single well-defined task. If a function is performing too many things, is doing too many jobs, perhaps it's time to think about dividing up that function into smaller functions. And one hint that your function may be doing too many things is that when you're trying to name the function, you're not able to properly express that in the form of a short enough name.